In this video, we're going to continue our series of looking at this idealized set of rate data in order to identify more information. Previously, we were able to use this to find K values for our forward and reverse reaction at 50 degrees Celsius, use that to find our equilibrium constant at 50 degrees Celsius, and determined out the equilibrium pressures of our starting material and our product. In this video, we're going to continue using this data, and we're going to solve the energy of activation forward, the energy of activation for the reverse reaction, and the delta H for the reaction. We're going to determine is this an endothermic or an exothermic reaction. If you want to give it a try, go ahead and pause here. But otherwise, let's dive into how this one would work. Well, how are we going to relate this? Remember that the natural log of our rate constant divided by another rate constant at a different temp is going to equal the negative activation energy over R, 1 over T2 minus 1 over T1. Our rate constants are related to our activation energy. In fact, that is what governs rates. The activation energy is the hurdle that our reactions have to get over. So our rates are dependent on the activation energy. Our equilibrium constants are dependent on the delta H of a reaction. And so if I want to solve the activation energies, I need some rate constants. If I want to solve the delta H of reaction, I may need some equilibrium constants. Well, there's a few routes we could go. I could go solve the equilibrium concentration at 25. I would need the K values, just as we used before. However, if I need those K values, I can plug those in to solve for energy of activation. So let's solve those K values first. This appears to be our first step. And so in this case, we're going to go and calculate out our 25-degree runs so I can have enough information. Because at the moment, if we want to do the forward, I have the forward at 50 degrees, which means I have 1 K and 1 temp. If I had another K at a second temp, I could solve for the energy of activation. And so we're going to need another K at another temp, and I have the runs for it. Remember that our rate is going to equal the constant forward at 25 times the N2O4 pressure. It's an elementary reaction, so it's just the starting material. There's just one of it in the balanced reaction. And since it's an elementary step, we are assuming I would just need it to the first power. As this is a first order, it's only a single N2O4 breaking apart, I can use the integrated rate law that the natural log of my pressure initial divided by my pressure at time is going to equal K times my time. For us, that's 0.500 divided by 0.4995 is going to equal K at 25 forward, and our time of 1 second. That's going to give us 0.001001 per second is equal to our K forward at 25. So we now know our K forward at the lower temperature, 0.001001 per second. In terms of our K reverse at an alternate temperature, well, the rate reverse is going to equal the K reverse at 25, NO2 squared. This one was second order, which means we need the second order integrated rate law to help us solve it. 1 over the pressure at time, 0.498168, minus 1 over the pressure initial, 0.5. That must equal KT. Since our time was 1 second, we can do the subtraction, divide 1 second over, and we will find that our K reverse at 25 Celsius must be equal to 0.007354 per atmosphere seconds. So we have our values. We can go ahead and calculate out our energy of activation. We're going to have to do this for the forward and for the reverse. Our two energies of activation will be different depending on which direction we are going. Remember, if you have starting material and product, or product and starting material, the energy of activation is going to be different depending on which direction you are going. Going to the lower energy molecule has a smaller activation energy than going to the higher energy molecule. So there's a different energy of activation depending on which direction you are describing. Let's go ahead and do the forward reaction first. Natural log of our K2, let's make our 50 degrees Celsius our second set. So 0.015692 per second divided by 0.001001 per second. Our units will cancel out. All that's going to be equal to the negative activation energy over 8.314 joules per mole Kelvin. Temps 1 over 323, our temp 2 is 50 Celsius, minus 1 over 298. Our temp 1 is 25 degrees Celsius. Rearrange all this to solve for the activation energy. What we'll find out is that our activation energy for the forward direction, because we're using our K forwards, is going to be equal to 88,100 joules per mole. So approximately 88.1 kilojoules per mole. Same process for our reverse constants. Natural log, we'll use the 25 for the 1 and we'll use the 50 for the 2. 0.019284 per atmosphere seconds divided by 0.007354 per atmosphere seconds. Again, our units will cancel. All that must equal the negative energy of activation reverse divided by 8.314 joules per mole Kelvin. 1 over 323 minus 1 over 298. Again, 50 degrees Celsius and 25 degrees Celsius. Calculate this out. Our energy of activation reverse will calculate out at 30,860 joules per mole, or about 30.86 kilojoules per mole. Our rate data allows us to calculate out our rate constants, and our rate constants and the temp at which they were calculated allows us to calculate the activation energy. There's two separate activation energies, the forward and the reverse, so we need to use the rates constants associated with that direction. And so here we've found those two activation energies. Now this leaves us a couple options for solving our last bit here. The last bit is to solve the delta H of reaction. I could use those rate constants to find the KEQ, and I could use the KEQ difference between 50 and 25 to calculate out the delta H of reaction. Remember that the natural log of your KEQ2 divided by your KEQ1 is equal to the negative delta H of reaction over R times T1 over T2 minus 1 over T1. Our equilibrium constants are dependent on the delta H of reaction, while our rate constants were dependent on the energy of activation of that reaction. If we knew a second equilibrium constant, we could calculate out the delta H of reaction. Being that we do have a second set of forward and reverse Ks that are K reverse here at 25 was equal to 0.007354. I could set up a ratio of those to solve KEQ at 25. And while we will do that, there's actually an easier way. Think back to our reaction and our energy, your starting material and your product. In this case, which will look like this, we know that we have to go up 88 kilojoules per mole for the forward reaction. So we're going to rise up, but we only have to go up 30.8 for the reverse. So we need a larger rise in the forward direction than we need in the reverse direction. This is an endothermic reaction. Most importantly, though, they're both going to the same peak. So this section, the energy of activation reverse, when we compare it to the whole bit here, which is the energy of activation forward, well, the only difference is this lower part. This lower part, this is the delta H of reaction, though. It's the difference between the products and the starting material, which means the delta H of reaction is just the larger energy of activation minus the smaller one. It's the total height minus the part that's just coming up from the higher energy molecule. So we could solve it by saying energy of activation forward minus energy of activation reverse, in this case, is going to equal our delta H of reaction. We can plug that in. 88.1 kilojoules per mole minus 30.86 kilojoules per mole is going to give us 57.24 kilojoules per mole. Using our energy of activation data we got from our rates, we can calculate our delta H of reaction as well. If we want to check this against the equilibrium option, well, then I could say that, hey, my K forward divided by my K reverse must equal my K of equilibrium. So at 25 degrees Celsius, we just solve those values. 0.001001 divided by 0.007354 must equal our KEQ at 25, as those are the rate constants at 25. This will give us a KEQ at 25 of 0.136116. If we plug those both into our equation here, natural log of 0.813741 divided by 0.136116 must equal a negative delta H of reaction over 8.314 joules per mole Kelvin times the difference of our inverse in temps, again 50 Celsius and 25 Celsius, so 323 Kelvin minus 1 over 298 Kelvin. Rearrange and solve for our delta H of reaction. Comes out 57,238 joules per mole, or approximately 57.24 kilojoules per mole. So from both directions, the differences in the activation energies or using the equilibrium constants that we could find from our rate constant ratio and plugging them in achieves the same value for our delta H of reaction. So there are multiple ways to have gone about solving this, and here we addressed several different ones. Identifying the activation energies requires us to use the rate constants. Rate is determined by the activation energy. However, the equilibrium constants are dependent on the change in enthalpy between the products and the reactants, the delta H of the reaction. Since rates at equilibrium and their rate constants are related, it is possible to jump between these different types of information as long as we set up our equations correctly.